Hi guys, welcome to another video. So today we're going to do possibly the uh, hardest, if not one of the hardest topics in the Extension 1 syllabus, and that's projectile motion. So last week we did forces, which was part of the applications of vectors topic. This week projectile motion. So projectile motions actually is in the old syllabus, but with the new syllabus, um, they've basically added an extra element with which uses vectors. So conceptually, it's the same thing. It's just different ways of seeing the equation. So this topic is going to be done in 3 parts. So today I'll show you pretty much the old syllabus way of doing projectile motions, and that's with the traditional horizontal and vertical formulae. Next time, we'll do the same formulae, but in vector form. So pretty much the same calculations, but a different way of seeing the questions. And then the third video, I'm hoping to do some harder questions. So just to illustrate why this topic's so hard. So today, the questions are going to be fairly straightforward. So basically, I say this to my class all the time, that maths gets really hard when there's ironically no numbers or very little numbers. So you'll see some of those questions where it's all to do with proofs and stuff. So we'll do that in video 3. So first topic, let me derive the formulae that you need, the common formula that you use, and then apply it to 1 or 2 questions, past paper questions that are relatively straightforward to do. So let's begin, shall we? So, and just to be clear, and this is quite an important point, in 3 unit maths, in extension 1, you got projectile motions with no air resistance, right? Because in 4 unit, what's new to the syllabus as of last year is that they basically put in projectile motions with resistance, which makes the formulae a lot harder to do. So for us today, just to be extra clear, and we will have no resistance with respect to air. Um, if you're keen to do some of those questions and you're doing extension 2, so I've got some videos already uploaded. Feel free to have a look at that and check them out just to see what type of questions or what type of formula you use. So for today, projectile motion with no resistance. So we sort of have a situation where an object, a projectile is, well, projected into the air. So what you'll see is that normally the questions will have some sort of element of initial velocity, right, projected. And also it's projected at some sort of angle there as well. Yep. So with that diagram in mind, it's a nice parabolic shape because of the lack of air resistance, right? So what happens in 4 unit mass is with air resistance working against you, you sort of get like it starts off parabolic and then sort of ends short, right? Because the air sort of stops it from going the full distance. Now, with this in mind, there are a number of equations, right? So the classic equations that get applied here that we need to know is, so I'll start off, maybe I'll call it formulae part I, all right? They call it the equations of motion. Now, when you look at projectile motion, the difference between this and what you've previously done in motion is that it's got 2 dimensions. It's got horizontal, which is x, and vertical, which is y, right? So we'll derive our formulae based on that. So a couple of things to note before I begin, actually. So we have gravity working downwards, right? And initially, so I'll put a little blue box here, right? Initially, and this is important because we're going to use this as part of our mass. Initially, so when t equals 0, right, 4 things apply. When t equals 0, 4, actually, I'll make that 6 things apply, right? So initially, we got acceleration, and everything sort of begins here, right? Initially, the acceleration, x, now the double dots mean, I don't know whether you've seen that before notationally, but that means acceleration, so that's 0, right? So initially, horizontally, you got no acceleration. Vertically, initially, you got gravity against you, right? Because if you're moving up, gravity is against you. So up is positive and hence gravity is negative. Now, velocity, these are important because we're going to use this to integrate later. So you can imagine that using your vector notation, if this is u, then, and this is y dot and x dot, right? So initially, if this is theta, you're using your SOHCAHTOA, you got x dot equal to u cos theta, and y dot equals to u sine theta, right? So we decompose, sorry, that's a theta there. We decompose the diagonal vector or speed or velocity of u into these two, right? And then distance-wise, and this is important, so sorry, displacement-wise. So displacement initially, now I'm going to put for this diagram, x is 0, right? And y is 0. But you know what? Y is 0 for this diagram only because it's on the ground. For our purpose, I'm just going to use a different color. I'm going to put h, right? Yeah, because it's not entirely, sorry, it's not always that we start projectile motion on the ground. Sometimes they'll project it off a cliff, in which case initially it's got a vertical distance. Also, sometimes you project from, say, below bottom of a hill, etc., where 0 is actually above it. So in which case the initial h is negative as well. So the h here denotes the initial height, yeah? And that's important. So I'll show you a question later where, actually no, the question later it looks like it's changing, but it's actually still at 0. But it's worthwhile. It's a worthwhile discussion. So here's what I'm going to do. So I'm going to move this topic a little bit over to the right. Give me a bit of space. Let's derive these equations. So everything sort of begins here, right? Everything sort of begins at your initial acceleration. So I'll begin with, maybe I'll do horizontally first. Yeah. You know what? How about this? I'll put down the formulae. All right, so you have all the formulae in one place, and then I'll prove it in the next slide. So horizontally, we start off with initial acceleration is 0. We will have to derive that initial, well, this guy over here, right? And then initial displacement, displacement across time. When you integrate this, you get cos theta t because that's constant, right? These ones here are pretty easy to prove. Vertically, once again, we start with the thing that's given, right? And that's constant over time. If I integrate this with respect to time, I get minus gt, right? Plus, now the constant over here that you'll find is u sine theta. So we'll use that to integrate later. And last but not least, if you integrated that again with respect to time, so get this plus u sine theta. And then just like before, so just like downstairs, I'm going to plus an initial height, yeah? So sometimes we'll need that, sometimes we don't. So this is the pack of 6 equations that some questions ask you to derive, some questions ask you to take it as given and then use it to prove subsequent questions, right? Now, off the back of this, can you see, right? The teachers call it a parametric equation, right? This equation is parametric because, and not Cartesian, because x is expressed in terms of another parameter t. And so that t here, oh, I'm missing a t from here. Let me just quickly slot that in, right? And so therefore, if I highlight that, the letter t here, right, is parametric. So if I solve parametric equation for t, I'll find Cartesian form, right? So if they ever ask you to express the equations of motion in Cartesian form, you basically solve the parametric equation. So easy. And if you do, so I'll leave that as equation number 2. I'll do that quickly later. Cartesian equation. You get, something that looks a bit messy, but not too bad. So minus g x squared on 2 u squared 1 plus tan squared theta. Now it looks a bit of a monster. and I guess to an extent it is. So that should say tan theta x plus, well, once again, I'll do it red, plus h if and when you need it. Yep. So once you do that, sorry, I'm going to move this a bit higher so I can fit all my equations nicely on the same page. Right. Now, most of the questions that you'll see would ask you to have either prove or they give you the Cartesian equation because it's a really nice equation. Can you see, right? A couple of things to note here. This is why this topic is amazing, right? It's amazing in terms of difficulty. It's amazing in terms of technical quality, right? Look at this equation. Can you see? In this equation, it's actually like a double quadratic, right? Depending on what the question gives you. There's a quadratic there in terms of x squared and x. There's a quadratic there in terms of tan squared and tan. So sometimes they might give you the value of x and ask you to solve for theta, in which case it's a quadratic, or vice versa. They give you theta and they ask you to solve for x, right? So there's a lot of variables here. Just make sure you identify them all, right? It's about 5 or 6. They're going to be part of why this topic is considered to be one of the hardest in Extension 1. So now, I'm going to give you 3 other formulae. The 3 other formulae is, it'd be good if you entered in the exam remembering these, but generally speaking, you can derive them. They're very common questions, right? So the first thing that a question might ask you to find is the total time of flight. So basically they say, how long did it take for the projectile to start and end? This formula here, so T equals to 2u sine theta on G, right? And then they might ask you, what's the total horizontal range, right? So basically, what distance did it travel when it landed back on the ground? Now, I say this to my class, you just got to be very, very careful with each one of these formulae. Can you see each one of them look very similar? They have u's and sines and 2's everywhere. This one's u squared sine 2 theta, right? Subtly different. Oh no, are you telling me I don't have a little bit of vertical space? Right, I'm going to access it because I've got one more formula to put in and I really want to squeeze it in there. So, and then max vertical height. So just be very careful with your formulas because they're subtly different, which is h equals to u squared sine squared theta on 2g. So there it is, guys. So these are the formulae. I'll prove them now and then we'll use them. Yeah. So be very careful with, especially the last 3. In a test, can you actually use them instead of like deriving from scratch? It really does depend on the question. So largely speaking, I always ask my students to derive from scratch, and then just if you memorize it, use your deriving from scratch use this as a check for that. So that's how we will do it. So let's prove the first part, right? So everything sort of begins, right? So maybe go proof. Everything sort of begins. Let's start with the easy one, right? Horizontally. Yeah, everything sort of begins here at the acceleration. Now we know to get from acceleration to velocity, we integrate, right? We integrate. So with respect to t, that equals to the integral of 0 dt. That's easy. That equals to just constant. Now, because there's going to be 4 sets of integrals, right? I'm going to call this constant 1. Yeah, and when time equals 0, I know that initial velocity is u cos theta. So therefore, if I sub 0, there's no t value, so I sub that in, c1 equals to u cos theta. Therefore, velocity horizontally equals to u cos theta. Pretty easy, right? And please note that for this one and this one, actually for everything here, if I have u, right, initial velocity, and I have the angle that I project at, I can get that value, right? So 1 down, 2 down, I've got 4 more to go, 1 more horizontal. So if I integrate this again, so x equals to the integral of u cos theta dt. Now, keeping in mind that u is given, theta is given, they're both constants, right? So if I integrate a constant with respect to t, that just becomes u cos theta t plus another constant of c2, and then I use, once again, when, right, the initial conditions over there, right, when t equals 0, I know that x starts at 0, so the horizontal distance starts at 0, starts at the origin. Therefore, if I sub-0 into there, sub-0 into there, you'll see that c2 is 0 as well. That's nice, because therefore my horizontal displacement formula is this guy, dt, times t, right? Pretty straightforward. Nothing too controversial there. Just integrating two constants, integrating 0 and then integrating another constant, right? That's pretty easy, right? So vertically. So we follow the same concept of just integrating twice, but when it's vertical, it's a bit more complicated because of the initial acceleration being negative gravity, right? So we start here. So first part, so we integrate negative gravity dt. Now that's easy because gravity is constant, 9.8 or 10 in the question. So therefore, this guy equals to minus gt, right? Plus another constant. And I know when t equals 0, initial velocity is u sine theta. So if you sub 0 there, sub in this guy into there, I got the constant to be equal to u sine theta. Right, sub that back in, and you go therefore initial. Sorry, no, I keep saying initial. Vertical velocity is minus gt plus u sine theta. Beautiful. There you go. Highlight that. Yeah. So now it's looking a bit more complicated, but the process is just integration. I know that this guy's linear, this guy's constant. So when I try to find my displacement, right, it's not, it's relatively easy to integrate because I know that this guy is linear. So just add 1 to the power, divide by new power. This guy, this, yeah, and then plus also t because it's constant plus your last constant. Now, like I said, just to be absolutely clear, right? If I have a situation where it starts on the ground, then when t equals 0, y equals to 0. But if I have a situation where it gets projected off a cliff, where that starting is h, then when t equals 0, y equals to h. Sometimes, and I'll put this over here as a comparative, right? Sometimes you might be projecting off a cliff, right? But they define the starting point here of the cliff as 0. In which case, in this case, when t equals 0, y also equals 0. It's just that the y value can be negative, right? Well, over here, if 0 is down here, the y value can never be negative, yeah? So there's a subtle difference. Just be very clear on, in this case, where the starting point is. Does it start at the origin or does it start at an elevated h value? So for this derivation here, how about I go when t equals 0, right? Y equals to, I'll put in h, because h can be 0, right? I'll put in generically h, in which case you can see that if that's 0 and that's 0, C4 is h. Therefore, my vertical displacement will be minus gt squared on 2 plus u sine theta t, and then plus h. I'll use it as a different color because sometimes the formulae that you'll see don't have that h value because they start from the ground, right? Or start from the origin. Guys, that's 6 equations to derive. The first 2 is given, so technically you're deriving only 4. That's how you do it. So easy questions in projectile motion generally give you marks for proving this, right? Because it's like, and it's quite textbook. So once you've proved this, let's quickly do the Cartesian and work out the other 3 formulae before I actually before I embark on doing 2 past paper questions, right? 2 past paper questions. So can you, yep, make sure you copy those down if that's what you're doing for this video. Yeah, is I think the best way to utilize these videos is actually copy these down into your workbooks or your theory books. So if I know, right, so maybe this is for the Cartesian equation, right? Now, if I know that x equals to u cos theta t, and I know that y equals to minus gt squared on 2 plus u sine theta t plus h, right? What I'm going to do, like I said before, this is parametric right now, and the best way to solve parametric equations is to basically make this guy the subject, make the parameter the subject, so t equals to x on u cos theta, and then drop this into the values of t there, in which case the t disappears and you'll have an equation with just y's and x's as the key variables, hence a Cartesian equation. So it looks a bit nasty when you sub it in, but it does clean up quite well. So sub in there, well, I'll say quite well, it's still pretty nasty, but you'll get what you want, all right? Plus u sine there times u x on u cos plus h. So a few pieces of cleanup here, right? You get minus g times x squared on 2u squared. Oh, did I forget the u squared in the other? Might have, let me see. Just make sure. No, I got that there. U squared there, perfect, good. Right, that formula, that Cartesian formula is where I want to head to, right? So on the bottom here will be 2u squared. Now, cos squared's on the bottom, that's important. Just to be clear, when I do clean this up, cos squared on the bottom is sec squared, right? If I put it back upstairs, reciprocal, sec squared is 1 plus tan squared, which is what the formula usually has, right? The plus now, in this case, the u's go away. Sine and cos is tan plus h. So the only thing left here to clean up is that cos squared there is, remember, sec squared, and sec squared is 1 plus tan squared, right? So therefore, my Cartesian equation will be minus gx squared on 2u squared, 1 plus tan squared theta. Oh, I wrote tan x, that's naughty. It's tan theta x, right? Yep, plus tan theta x plus h. And there's my double sort of quadratic equation again, right? Quadratic in terms of x, quadratic in terms of tan theta. Yeah, very, very important formula. So please make sure you understand that, solving parametrically to get Cartesian. And then that leaves me with 3 other formulas to derive, just to show you, in deriving the next 3 formulae, it's actually teaching you how to do those questions if they arise, because generally speaking, you will do these from scratch. So, right, first one is the total time of flight. Okay, so just to be clear, this is basically saying, if this is t equals 0 over here, so this is t equals a capital T, right? That's what I want to find. So what do I know at this point, right? What do I know happens at this point? At this point, vertical distance is 0, or vertical displacement is 0, right? So I'm going to sub in 0 to find an expression for time. So don't sub it into Cartesian because there's no more t variable. Sub that into the displacement formula up here, right, for y. So in this case, when y equals 0, if I sub y equals 0 in here, I have, now, I think sometimes people, there's so many things here, people miss the woods for the trees, right? What you got to see is that it's a quadratic equation, isn't it? Yeah, that's just a simple quadratic. Can I ask a favor? In this case, let's start from 0, in which case I'm going to sub in 0 into h, right? Just to show you that, you know, if it's 0, this is how you do it. Otherwise, you got to solve a messy quadratic, which is fine, right? But most of the questions look like this when it comes to total time of flight. Now, if you were to solve this, can you see it's a quadratic? What am I trying to solve for? Time, right? T. So if you were to solve this, you basically factorize the t out from both sides. Oops. So in this case, assume h equals 0 as well, right? Just over here, h equals 0 in my formula, right? Just before you're like, where'd h go? Because it starts on the ground, h is 0. Now, when you factorize this out, you still got one more t left in this, so minus gt on 2 plus u sine theta equals 0. And when I solve this, I got t equals 0, right? Which makes sense because that's the first time it's on the floor when y is 0. And the last time is when I try to solve this monster, right, I get minus gt on 2 plus u sine theta equals 0. And guys, if I make t the subject there, I get, therefore, I'll put it as capital T because that's my solution. This guy goes over times 2, so it'll be 2u sine theta on G. Yeah. So let me quickly check that on my first page there. 2u sine theta on G. Perfect. Yep. So pretty straightforward, hopefully. Not too bad. Just subbing y equals 0 and solve a quadratic. Now, if the question has numbers, obviously this question is much easier, but without it, that's how it looks like. That's how it looks like. Next thing now, do I have space? You know what, can I ask a favor? I am going to move this over. Yep, I'm going to move this over to a next page because I like when the three formulae sort of form part of the same theory point. So maybe I'll leave that here. That's total time of flight. Let's come over here. Horizontal range. Now you can see for horizontal range, all I gotta do, right, is basically from here to here, this distance here is a horizontal range. What does that mean? I basically would sub in, so this is x equals 2. I'll sub in the total time of flight into the horizontal displacement formula, right? So I know that when t equals to t, right, the horizontal distance or displacement formula is u cos theta t, right? So I'm just going to replace capital T, right, into here. And I know that capital T, which is total time of flight, is this guy. Sub that guy in. Yeah, sub the total time of flight into the horizontal displacement, and you should get it. Therefore, horizontal range equals to u cos theta times 2u sine theta on G. Now, hopefully, you guys are on top of your trig double angles. 2 sine cos is going to be the double angle of sine, and then there's u squared on top as well, so it'll be u squared sine double angle on G. Is that okay? Pretty straightforward. Last but not least, the maximum height or vertical height attained, right? So max height. So this is vertical, right? So diagrammatically, I have a projectile and the max height is there, right? And I need to know that. Now, what happens, guys, at this one? Over here for this one, I should really say time equals to capital T, just to get the diagram working. What happens at max height? Now, you can do this two ways. You can either say, well, because it's symmetrical, max height occurs at half of that total time of flight, and you sub that time into the y displacement. Alternatively, what else happens at the max height? Vertical velocity is 0, right? Because it comes to a standstill vertically, right? And then drops back down. So vertical. So firstly, this is what I'm going to do. I'm going to sub in 0 into vertical velocity and find the time when that happens. You'll see that it's actually exactly equal to half of total time of flight. And then I'm going to sub that into the vertical distance, right, to find the actual height itself. So it's a two-step process. So step one, when the vertical velocity is 0, so remember vertical velocity is equal to minus gt plus u sine theta, right? And if you made t the subject there, so when this is 0, then that equals to u sine theta on G. And guys, look at that, right? That is exactly the same as the capital T here, total time of flight, but without the 2, which means it's half, which makes sense. Total time of flight, because it's symmetrical, half that time would be when I would reach max height, right? So using this, yeah, that's the time. So over here, right, to get to this point here, time equals to u sine theta on g. I'm going to sub this into the y value now, the y displacement, which I have up here, right, into that guy to get my max height. So therefore, maybe I can fit it on here. H equals to minus g on 2u. So 2u. Nope, no u there. I'm thinking about the Cartesian. Minus g on 2 t squared. So this guy squared u sine theta on g squared plus tan theta. No, I'm thinking Cartesian again. It's just u sine theta times u sine theta on g, and assuming height is 0, right? That's the formula. Let me quickly check that upstairs. The minus gt squared minus, perfect, right? Now you can sort of see that there's a bit of algebra simplification here. That g and one of these goes away, so the top just becomes minus u squared sine squared theta on 2g plus, now it's no coincidence, u squared sine squared theta on g. Guys, if you can sort of imagine, this is like a full value of u squared sine squared on g. This is like negative a half of the same thing. So I know that if I put them together, right, what it's basically like negative half plus 1, which is like a half. So therefore, h is half. So u squared sine squared theta, and the way you express half is just 2g. Right? And that is your total, your max height. So they're the key formulae, the 3 key formulae, Cartesian and the 6 equations that you'll use in this topic. Yeah? Keep that in mind. Let's do some questions, right? So I've got 2 prepared for you. So the first one I'm just going to drop in, right? It's from Caringba, past paper 2009, and it looks a little bit like this. So I'll zoom in for you to have a read, right? So let's unpick this and actually do it. So like I said, ironically, in 3 to mass, when it's got math like numbers, it's actually easier. When it doesn't have numbers, it's actually much harder. Right? So this one, a missile is projected with the speed of 50 meters per second at an angle of 45 degrees. It is aimed at a tall building, which is at a horizontal distance of 200 meters from the point of projection. Right. So let me just highlight some key words. I've got speed, initial speed. I've got angle of elevation. So just to be clear, that is u, that is theta, and then this is gravity, right? So gravity is defined as 10. Show that. Now, what am I finding? What's my question? So I need to find the equations of motion, right? Yep, I need to find I got to actually use integration to prove that and that, right? That's what I need to do. Now, next one, total time of flight, and then height, right? Classics, right? Total time of flight. So this guy here is capital T, that guy there is capital H, right? For 1 mark each. So a classic question. So part 1. So I know, right, in this question, because they're asking me to derive for 2 marks, I can't just use it, right? I got to actually say, well, horizontally, x double dot is 0, and then I'm going to play the integration game. But the only difference is that they gave me some exact values, right? So I know if this is a start, then x dot equals to the integral of 0 dt, which I know to be first constant, right? And when t equals 0, well, I know horizontally the formula there is cos, u cos theta. So in this case, it's u, which is 50 cos 45. Guys, cos 45 is 1 on root 2 or root 2 and 2, so that's going to be 25 root 2 as an exact value. Is that okay? So therefore, horizontally is 25 root 2 as a constant. So let's power through this. So integrate that constant for displacement, which is exactly, you can see it there, right? I just hacked on a t. So therefore x equals to 25 root 2, because it's constant, hack on a t plus constant of 2 when t equals 0, because it tells you it starts off, does it start, I'm assuming it starts off on the ground. So when t equals 0, x equals 0, pretty easy. C2 is 0, right? So therefore, yep. So, yep. X equals to 25 root 2 t. Perfect. So I'm assuming in terms of marks, that's 1. It's a lot of work for 1 mark because it's only worth 2 marks, right? Now, it's because it's so textbook, right? It's a bit tedious, but because it's so textbook, it shouldn't be worth that many marks, I guess. Right, I'm going to do exactly the same now, vertically. All right, let's do this. So start off with the negative gravity. So I know it is negative 10. Yeah, gravity given in this case. So I know integrate that. dt negative 10 is nice because then it becomes negative 5 t. No, negative 10t. Yeah, plus your third constant when t equals 0, u, no, y, sorry, y dot equals to u sine theta. In this case, actually exactly the same, right? So 50 sine 45, and I know that to be 25 root 2. Sorry, that's my constant. Yeah. So y dot equals to so initially when t equals 0. Yep. So if that's the case, then sub that in. I got therefore, yeah, that's my constant. That's my C3. Y equals to negative 10t plus 25. So let me write that better. My t's will go pluses. Plus 25 root 2. Cool. Sorry, I forgot the dot there. So okay, so all I've done is integrate, find the constant, sub it in, and then basically that is what I just copied and pasted. And last but not least, y equals to the integral of minus 10t plus 25 root 2 dt. Integrate that. Now that's a linear expression, so add 1 to the power, divide by nu minus 5t squared. That's constant, so 25 root 2 plus the last constant of integration. Now, it doesn't really say that it starts at, or does it? Let me see. Here. A better phrased question would say that it starts on the ground, but let's assume that when t equals 0, y equals 0, in which case the whole constant disappears. Therefore, y equals to minus 5t squared plus 25 root 2. Yeah, it's very long-winded. It's 2 marks, but there it is. Yeah. Now for part 2 and part 3, let me ask you a favor. Right? I'm just going to use a formula. They all start from the ground, so I'm just going to copy and paste. Worth 1 mark. I mean, how many marks can you lose? I guess if you use the formula. So far, part 2, if you want to do total time of flight, yeah, from scratch, you get it, or it's 2u sine theta on g. Now I always remember these wrong, so I'm just going to quickly check. 2u sine theta on g. You know what? Let's be sneaky. I'm going to copy these. Let's just paste it in. Have them as formulae. Beautiful. So in this case, it's going to be 2 times 50 times sine 45 all over gravity. Yeah. So what's that? Boom, 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 boom. Looks to be, I was hoping for an answer. So if I punch it in calculator, that's 110, 10, 100, 10 sine. So 5 root 2, is it? Seconds. Yeah, can you check that for me, please? Let me have a quick gander to see whether it's available. No, it's not in the solutions. Strange, they didn't do the solutions. That's okay, right? Yeah, I think it's 5 root 2. Part 3, what they asked for. Find the height I'll find the height when the missile. That's not h at all. Oh man, or is it? I don't know. But it says find the height. So I immediately thought it was max height when it hits the building. When it hits the building. Now, what does that mean? It's actually easier because it basically says it hits a building at 200 meters, right? So find when x equals to 200. They want y value, right? So this is what I'm going to. It feels like a two-step process. I'm going to find the time it took for x to be 200, and then sub that time into y. Easy, right? So sub x equals to 200. So if x equals to 25 root 2t, I'm going to sub 200 in here. Yep, and I got t equals to, what's 200 divided by 25? 8? Yeah, is that 8 on root 2? Move it up slightly so I can fit the fraction in. So it'll be like 8 on root 2. Yep, and then I sub that into the y value. Is that right? Yeah, so let's see. So what's my y value? So I got y equals to minus 5t squared plus, should be a t there, 25 root 2t. It's like solving parametrically, sub that and that, or replace that with this guy. To there, into there. So you get minus 5 h on root 2 squared, 25 root 2 h on root 2. Now I didn't rationalize that because I know it's going to cancel out. So I believe if you did this well, let's see, I'm going to access my calculator here. Minus 5 times 64 on 2. Root 2 is cancelled out, plus 25 times 8. 40 meters. Can you check that, please? Not too hard when you have the formulas, and it's the same. This is like, you know, can't be more textbook than this. If they give you numbers, super easy, right? Let's do one more of this sort of caliber. As in not too hard. So this one, the next one here, let's do one more question from Hornsby Girls. Hopefully that was all right. So Hornsby Girls. So this one here, a cricket ball leaves a bowler's hand 2 meters above the ground with velocity of that. So in this case, it's very important. Now, it looks like it's got a starting elevated height, but it doesn't because they defined the origin to be 0, right? And the ball travels negatively from that 0. So just keep it in mind. So h is still 0 in this case. All right, what do we have here then? So 2 meters velocity, 5 degrees, right? 5 degrees at an angle of 5 degrees. So initially, it starts projecting at 5 degrees, right? So let me just circle that. That is u. That is theta. Yep. Classic. Oh, they didn't give me gravity, have they? Huh. No gravity. Okay, I'm going to assume 10, I guess. Is that right? Yeah, looks like they've assumed 10 as well. So can you please assume that gravity negative 10? Let me just see. Normally they give it to you. Yeah. Okay, cool. So find the time when it strikes the ground, right? So over here, find the angle, which is that's new, and then show that the ball is parabolic. So even though it's projecting, so basically, if you can show Cartesian is a parabola, it's a quadratic, you're sweet. So let's see this. So firstly, goes find time. Secondly, find angle when it strikes the ground. So we haven't done that yet. It's not too bad actually. And then thirdly, we show that it's Cartesian. So part 1. Find the time when it strikes the ground. So what do we know when it strikes the ground? We know that the vertical distance. Now, normally, if it's got a height and then strikes the ground, y equals 0. But in this case, they define the initial height to be 0. So when it strikes the ground, y equals to -2, right? So for the first part, subbing y equals -2 into the equations. Oh, can I use them? I do not prove these. See, I love these questions. When they ask you not to prove, right, it means you can take these for granted, right? Use them. Yep, so let's use them. So for the first part, find the time it takes to hit the ground. It feels like I'm just going to sub in -2. So into the y, I think that's exactly what you do. You just got an ugly quadratic to solve, right, for t. Sine 5 degrees there. Yeah, it's very ugly. What the? I know why they didn't give you gravity, because they're not asking you to derive the formula. They're just giving you the formula, right? So you don't need to derive. But they assumed gravity to be 10. So, all right. Wow, that is not nice. So it's a quadratic in terms of t. So let's bring everything over. 5t squared plus 30. Oh, that's not a minus. Oh, it is minus because good. There you go. Perfect. All right. 30t sine 5 degrees minus 2 equals 0. Sub into the quadratic formula, which isn't pretty, but it's just, you know, calculator work, sine 5 degrees plus minus. Now, obviously the minus case would be when it lands backwards, right? So I'll put plus minus there, but we're only going to use a plus. So 3 sine 5 degrees on your calculator squared minus 4 AC all over 2A. So if you did that, I think it's about 0.4 seconds. Yeah, perfect. Not too bad. Let's move on. Now find the angle at which it hits the ground. This one here isn't obvious, right? It's not going to access any of the formulas we use, but basically when it hits the ground, right, I'm just going to zoom into that diagram there, right? So I zoom into that diagram, when it hits the ground, right, the way you sort of do it is that you basically work out, using SOHCAHTOA, right, the velocity vertically and the horizontal velocity, right? And I'm going to call this angle here theta, right? So it's a bit small there, but basically using this expression, I'm going to be able to find the angle at which it hits the ground, right? Using SOHCAHTOA. So I need an expression for the velocity vertically and an expression for the velocity horizontally. So I know that the way I'm going to do it is tan equals to opposite over over adjacent. Now this formula here is, it's not given here at all. So I'm just going to, the reason why it's worth 2 marks is because I need to differentiate that y value there to get the velocity formula, right? Because the velocity is the thing that is diagonal here, right? So find the angle at which it strikes the ground, and we use velocity to do it. So use velocity, not displacement, right? Use velocity. So y, differentiate this with respect to time, it's minus 30 sine 5 degrees and minus 10 times t all over. Now, what is that t? It's a total time of flight. I'll sub in 0.4 in a second. Over x dot. So I'm going to differentiate this guy. 30 cos 5 degrees, right? So once you do that, I want to sub in this time because it's the angle. So basically, you can imagine this formula is the angle at each point on the parabola. But if I want it right when it strikes the ground, I sub in the time that it took to strike the ground, which is 0.4. Sub it in your calculator. If you shift tan that or inverse tan that, I believe the answer is, so if you did that, now because of that negative, you're going to be basically finding the obtuse angle, right, against the horizontal. So I think it's like 168 degrees ish. Now, so if you did that, that's perfectly fine. The question doesn't say acute, so I'm going to leave that as my answer. If you did 12 degrees, so the other side is equally right. So whether you do 164 or 12 degrees, I think both of them are equally acceptable. Right? It just depends whether like if you have a line that strikes the ground, whether you find the obtuse or the acute, right? It's entirely feasible to be able to derive either. So part 3, last part. So all they're asking for is to show that the ball is parabolic. I'm going to solve this parametric equation. So I'm going to make t the subject, right? So from the x value, I know that t equals to 30 equals to x divided by 30 cos 5 degrees. And then I'm going to sub this into y equals to minus 30t sine 5 degrees minus 5t squared, right? I'm going to sub it into, so here it is. I'm going to sub this into, went too far. The values of t there, t there. Now, the moment I sub it in, I'm probably going to get a quadratic, and then I can conclude that it's parabolic. So I'm just going to move this up so I have a bit more vertical space. All right, let me zoom out. Let's do it. So I want this in here and here. We've done this before. This one has numbers. Shouldn't change your process that much. So 30 times x, 30 cos 5 degrees. So that's the tan values. They've just rearranged it right backwards. 5x on 30 cos 5 degrees squared. That's the sec squared one, right? So in this case, 30 goes away. That becomes tan, right? Let's clean this up. That equals to tan, negative tan, and 5 degrees x. So that's my tan value. Normally I have that at the back. Same thing here. So this one here, minus 5x squared all over 30, I think it's 900 cos squared 5 degrees. Now I don't really need to do much more than that. I can just leave it. I don't need to make it tan squared because all I need, right, to prove that it's parabolic is x and x squared here. I'll simplify that 5 on 900. So therefore, y equals to, I'll put that first, negative x squared 5 on 900 is like what, 180 cos squared. I don't need to make it sec squared, right? Or sec squared or tan squared. I'm just going to leave like that, minus 10 5 degrees x, right? And that's my answer, which is parabolic, right? You can say which is parabolic. So, guys, hopefully that was okay. That last question had a few new elements. So Cartesian, they call it parabolic. Finding the angle, we're going to use the vector, the diagonal vector of velocity, break it down into horizontal and vertical components to find the angle at which it hits the ground. Very common question, by the way. Everything else, as per what we did. So that's the first video of projectile motion. I'm hoping to do at least 2 more, one with vectors. That's a new way of expressing these questions in the new syllabus. And then I will hopefully do some harder questions with very little numbers, right? Hopefully you like that video. If you liked it, please subscribe, like the video, tell your friends, and I'll see you guys next time. Thank you.